All right, here's the second one. So if you would write it down and give me a sketch of it. And this is another classic. So a 6-foot man walks away from a 15-foot lamppost. At what rate is the shadow, this is the man's shadow, lengthening when he is 20 feet away and he's walking at a rate of 4 feet per second? So take a second and sketch the picture. Pause it, see if you can get something similar to what I have. Alright, so here's the 6-foot high man. Alright. Alright, so this man is 6 feet high. This lamp post is 15 foot high. And we're looking at a shadow. So a shadow occurs when the lamp post hits the man and creates a spot right there. So the shadow will go from his feet to that point. And as he walks away, the shadow will change in length. So I'll call this S for shadow. And we'll probably need this distance here. I'll call it X. All right. So let's, first of all, if you would answer for me, what derivative is the question asking for? Remember, it's a rate of change. So what rate is the shadow lengthening? So did you get ds dt? The change in shadow with respect to time. So that's what we're going to find. When, there's always a when 4 feet per second, when he is 20 feet away. So it's when this value, when x equals 20. All right, so hopefully you could see that coming. So what relationship this time? I reckon that a right triangle would be useful, but we don't know this, we do know this, and we don't know that, we don't know this, we do know this, we don't know that. So it doesn't seem like there's enough information for a Pythagorean theorem. So do you see another relationship from mathematics that relates these variables? That is going to be similar triangles. So we can say this is to this as that is to this. So 15 is to this side, s plus x, as, so that's our equal sign, 6 is to s. So far we've used Pythagorean theorem in these problems and similar triangles. So those are typical. And so I'll show you all the typical ones, but not all in one night. This will be all for tonight. So let's start, before we take the derivative, let's clean this up a bit. It's a proportion, so we can cross multiply. 15s is 6s plus 6x. Move the 6 s's to move like terms together. So subtract 6s, you get 9s equals 6x. Since we're looking for ds dt, I want to leave s in my problem, so I'm going to solve that for x. Divide by 6 and reduce. 9/6 is 3/2. S equals x. So that's a pretty decent equation to take the derivative of implicitly. So going from left to right, the derivative of 3/2 s, see if you can get that. It is 3/2, but then it's followed by using the chain rule by ds dt, which we have to do for all our variables. And when we're working with time, and then dx, the derivative of x is 1, but we need, using the chain rule, dx dt. All right, so we should know all those variables except the one we're looking for, which is this one. The only other one we need is dx dt. What's the change in this x as time goes by? We found out that it was 4 feet per second. So 3/2 ds dt equals 4. Solve that for ds dt. And you get 4 divided by 3/2 is 8/3. And that's the change in the shadow's length per time is 8/3 feet per second. All right. These are very, very repetitious. You always find out what derivative you're looking for when you find an equation that relates the variables. You implicitly differentiate it and sub in what is known and find what is not known. All right, so get that down in your comp book for a good reference, and we'll start introducing those problems in the bright and early morning. So till then, good night.